and welcome to the measure phase part 1. At this stage of the DMAIC project that you'll be working on, you're getting ready to actually measure some of the critical characteristics of your process, some of those critical outputs, just to see how good or bad your process is performing, so you can start to figure out how to fix it. So let's get right into it. So in order to understand the measure phase, it's important to always bring things back to the customer. Okay, so recall this concept of the VOC, or the voice of the customer. Every process that we work on has a customer. It could be an internal or an external customer to the business. It could even be a machine. Okay, it doesn't have to be a human. The customer is the one that defines the value for the process. Okay, so they are the ones that, if you remember those 8 wastes, they're the ones that define what is valuable to them, and anything that's not valuable is going to be one of those 8 wastes, right? Each step of the process should add value for the customer. Obviously, if it doesn't, then that's something we want to address because it's not something the customer values. They're not willing to pay for it. Therefore, it's an inefficiency or a unwanted cost, right? So remember we did the SIPOC, and so this is essentially something that we need to keep in mind for this step of the process, because we now need to start understanding for each of the steps in the process, what are those key inputs and outputs of each of the steps, and are there particular outputs that we need to measure to say how good or bad is the process. Okay, so how do we go about collecting voice of the customer, or VOCs, as they're typically known? There's lots of different ways to do it. Really, if you really want to understand the customer's perspective, that often can be done through surveys. Maybe you need to actually launch a survey with your customers to understand a little bit more about your problem. If you've got a defect that occurs in your product, it's not a bad idea to speak with your marketing folks. Maybe you need to run a survey to understand a little bit more around what their perception is around the product quality or around that output. It just depends on the type of project that you're working on and the type of problem. Maybe you need to survey some of your internal employees around a specific problem that comes up all the time. Maybe you need to do more focused focus groups, like more specific focus groups with small groups of people to understand the problem. In some cases, in transactional environments and whatnot, you may also end up doing individual interviews of people that are part of the process to start to uncover some of their needs, some of their challenges, and in essence, you're going to find a lot of pain points. Okay, you're going to be doing an awful lot of listening here as opposed to talking. So you want to listen to what the customers are saying about the process, and there may already be existing information. Maybe there's data, maybe there's other anecdotes that have been, given about the process and how it performs. Okay, so there's various different ways to how you collect VOCs, all of which are quite important. At the end of the day, the VOC is the qualitative expression of what the customer wants. And there could be more than one VOC. It's not just one VOC for your problem or project. Now, the CTQ, if you recall, which is short for critical to quality characteristic, the CTQ, how it's related to the voice of the customer, is that the CTQ is actually the quantitative measure of that particular VOC. Okay, so the VOC typically is a qualitative measure. The customer might say something like, hey, you know what? I would like my cup of coffee warm and fast. The CTQ is really the specification or the characteristics such as time or hot or cold temperature, for example. Okay, and then of course the final distribution you see on the right there is the voice of the process. So how well are you meeting that customer need? Now you're bringing into things like specification limits. Okay, so for example, when you get to the voice of the process, you might now have to understand, based on what the customer wants and the fact that we're measuring things like temperature or time for a cup of coffee, what are the customer's expectations that will drive a spec? Something like, I want my cup of coffee no later than 3 minutes from when I order it. I don't want it to be above a certain temperature or below a certain temperature. So now you're starting to put in certain specification limits, and that's how all of these things are connected, because now you can see that you can go and measure your business process to say, how well am I meeting my customers' CTQs, which in essence will meet or exceed or not meet the voice of the customer. Let's look at the 4 parts of a CTQ. And for every CTQ that you go and gather about your process for your specific VOC, each CTQ will have an attribute. And in the example of the cup of coffee, that attribute could be volume, it could be time, it could be temperature. Okay. And of course, in addition to the attribute, you need some sort of a scale. So how do I measure that attribute or that trait? How do I measure temperature? How do I measure time, right? So seconds or minutes, and of course, Fahrenheit or Celsius for temperature and so on and so forth. Okay. So a scale is important. Then, of course, you need a standard. So what is the standard that the customer is demanding? Is there a specification that they demand? Do they say, hey, listen, you know what? I don't want to wait for a cup of coffee much longer than 3 minutes. Maybe that's the upper spec limit, right? They want the cup of coffee to be hot, but not too hot and not cold, right? So they might give you a specific specification. And then final thing that the CTQ has is some kind of data type. So you're gathering information, and that data type could be a quantitative measurement like time or Fahrenheit, or it could be something like an attribute or a discrete measure such as good or bad. Maybe it's a specific color. You want it black, or you want it white, or you want it, with a little bit of milk, not enough milk. So there are different types of data that may or may not be quantitative in nature. So when you get into the measure phase, there's 2 key areas that are going to be extremely important for you. The first is the type of data that you're dealing with, and then of course the second is how best to take a sample. Okay, so in order for you to assess the performance of a process, which is one of the key aspects of the measure phase, you're describing how bad my problem is, where is it occurring, how long has it been going on for, that sort of thing. You need to collect data and compare it against some kind of a standard. Okay, now, in order to gather data, there are 2 different kinds of data that you might face, as I just mentioned. You might find discrete data, which with your process, and that might be related to a particular VOC, and that's something I mentioned before. Maybe you have to measure how often you're getting the cup of coffee correct to order, right? That's not really a quantitative measurement. I can't put it on a scale and measure, there's not some metric around there. But what it is the number of times. It's count data. It's the number of times you get the order correct, or the percentage of time that you get it correct. So that's technically called a discrete measurement, and it requires a certain type of sampling and a certain type of way of visualizing the data. Okay. And contrast that to the most common data that you typically are used to and you see, which is continuous data, which is a measurement, right? So it is a temperature. So if I take the cup of coffee, measure the temperature, I can measure that on a scale, okay? Or I can measure the time on a scale. These are quantitative measures, stuff that you're normally used to gathering, okay? So those are the 2 types of data. Very important to understand the differences, and we'll talk more about that in a moment. But when you go and collect the data, you need to come up with what's called a sample size. And so the sample size, certainly you're not going to sit in this example of a cup of coffee and measure every single person that comes and orders a cup of coffee from now until next month or even a year from now. So you can't typically take 100% sample. It's very difficult to do that. So that means you need to take a smaller sample, a subset of that 100% of people that order coffee. So you need to figure out what's the best way to sample. So the most common question we always get is, how often should I sample? How much should I sample? And when should I sample? So there are lots of things that go into this. It's not a quick and dirty answer, but you really need to understand the best way to figure out how to sample is to understand some idea of how the process might vary. Maybe the team has some indication that, from one day to the next, at this coffee shop, we expect that Mondays are worse than Tuesdays or worse than Wednesdays. So now you know that maybe the day of the week is something that there's something there as to root causes, right? So you would want to sample across those days to say, what does Monday look versus Tuesday versus Wednesday? Or when you gather your sample, make sure you include that. Make sure you might include other things that might cause the variability. Maybe it's the person that's taking the order or the barista that's making the coffee, in which case now you want to sample and make note of which person is making the coffee each time, so that then you can start to do some analysis in your analyze phase to really dive deep into these areas. So sampling is a very important part. Highly recommend that when you get ready to do some sampling, it's something you sit down with your coach so that you can go through some of these exercises to figure out how to sample, how much to take, and when to take it. Okay. And then finally, when it comes to sampling, there are these two types of sampling. So the second one there, called rational sampling, is very similar to what I just mentioned. So when you have some access to the process, so you've got access to the coffee shop or the coffee making process, when you have access to it, you can sample it at different stages of that process. So I could take a sample on various different days of the week in the coffee shop. Maybe I could take the sample by different operator or by different time of day, something like that. So you have access to the process, and when you do, and you take samples according to that process, that's called a rational sample, and it's very powerful to do that. The other type of sampling procedure is called a random sample, and this is typically only deployed when you have no access to the process. So the best way best example I can give here is, let's say you're a food company and you're making a particular product, and then you ship it out into the world, and you're shipping millions of products out into the marketplace, into the stores, and you want to measure, let's say, the amount of shelf life, right, of that particular product. If I didn't have access to the process, what you might have to do is go into the stores and take a whole bunch of samples. And that's really called a random sample, because you don't know when really you didn't have access to the process, what part of the process made what, when it was kind of done, that sort of thing. You don't have access to any of those things. So you're sampling at the end of the line, at the very, very end state of where the customer sits, and you're taking that sample. So sometimes you have no choice and you have to do that, but 99% of the time you do have access to the process, and I would highly recommend you take a rational sample. It is much more valuable to try to fix and identify root causes than a random sample is. So again, when you're in the measure phase, it's important to really baseline your business process, your process in question that relates to your problem. And so this slide that talks about something called big Ys, little y's, and process X's is related to your baseline for your measure phase. So what does that mean? So this is a bit of a busy slide, but essentially what this, imagine the white boxes in the middle of the page here that represent really your various process steps in your business process. And then, of course, each process has inputs and outputs, as we know. X's are typically referred to as inputs to the box. And then you have outputs that are Y's coming out of each of the box. And then at the end of this huge kind of yellow chevron, if I draw kind of a circle around your entire process, you have something called a big Y. So a big Y is essentially the big output that you're measuring. So if it's a manufacturing process, maybe it's efficiency, maybe it's first pass yield, quality, that sort of thing. A really big output. Maybe it's even time, lead time, okay? But then you've got little y's in between. So if it's efficiency, you might have an efficiency of each of these steps, right? Maybe you've got a quality metric of each of these steps as well. So those are kind of little y's. And then, of course, you've got x's. That you'll get to the x's in the analyze phase. Now, why this is important is that, typically Y is always a function of X, or your X's. Okay, so your output, your big Y, is always going to be a function of all of your inputs, or at least a certain number of inputs. So if your performance of your process is poor, which is probably why you're working on a project, that of course is the big Y, and it is going to be a function of certain X's. You and your job of the team is to find out which X's are contributing the most, which inputs are contributing the most to impacting that output, okay? But the goal of the measure phase is really to focus on these big Y's and possibly some little y's to measure and baseline and say, how bad is my process? And how, maybe what does the efficiency look like of some of the internal steps, or maybe what does the quality look of some of our internal steps? Okay, so hopefully that makes sense. Next, I mentioned we get into a little bit of a deeper dive on the types of data, and this is now a deeper dive on the discrete data. Now recall, Discrete data is basically a count data, or the frequency of something happening. It's either good or bad, or it's pass-fail type of data. Maybe you've got an invoice of some kind and the fields have been filled out incorrectly, and your project is to figure out how do we fix this invoice defect issue. Well, those are typically going to be discrete data that you're dealing with. It's not something I can put on a scale and measure. It's either good or bad, or you might have multiple defects with that invoice, but that's really called discrete data. And some of the challenges with discrete data, it's not that you shouldn't use it, it's just when you have a discrete data situation, it becomes a little bit more difficult to handle. How? Well, it might be easy to measure, but when you want to start understanding a trend of how bad is it looking, it becomes a bit more difficult to understand trends with discrete data. You don't really get any guidance as to kind of what went wrong. Okay, so when you get into the root causes, it can be a little bit more challenging dealing with this type of data. And then the other thing, the most important thing to think about with discrete data is, in order for you to really get a good understanding of how good or bad your process is, you often need to collect a lot more of discrete type data than you would if it was an actual measurement. So if I was measuring time, temperature, that sort of thing, you actually don't need to take that much of data to measure it to figure out what the average is and what your standard deviation is and how bad your process is. With discrete data, without getting into all the statistics around why this is the case, just know and reach out to your coach, but you will have to gather a little bit more data than you would get if it was actually continuous data. So if you had a choice, I would go with continuous data if possible, but if it doesn't exist, well, that's fine. You just use with what you got and keep it discrete data. Now, here's an example of a discrete data check sheet, right? So maybe you're putting in a check sheet to measure the number of errors on an invoice. And in this case, they're basically just counting the number of errors, that number of times you have the wrong date or the wrong name or the wrong payee on the invoice. And you can see that they've tracked it from week 1 to week 2 to week 3, and they basically can then sum it up. They can do what they want with it, okay? Now note that when we talked about the different types of sampling, this is actually a combination of both rational and random sampling. Why? Because you're basically waiting for the invoice to be created and to have the error on it. So now that's kind of the random sample. You're just taking any invoices that have been that have errors on them. But what makes it rational is they're gathering information by week, okay, by week. So now you can start looking at it over time. You can also start looking at it, well, whereabouts is it occurring? Is it the wrong date? Is it the wrong name? Which one is the more common error? So that makes it a rational sample, okay? So it's starting to make your life a little bit easier to understand where the root causes are for this particular process. Now, when you have a discrete data like that, as part of a Lean Six Sigma approach, sometimes it's important to actually calculate something called a defect percent defective, or a defect rate, or even something called defects per opportunity. Now, why is that important? Well, it then allows you to compare this process versus another process. Let's say you've got 2 different processes that have different products, but you want to be concerned with which one is actually performing better than the other. They might be completely different widgets, but now if you transform it into some kind of a metric that's called a defect per opportunity, then you can compare those quite discrete processes to each other. So what do you need to do that? Well, you need the total number of defects. You're counting however many defects as part of your sample. How many units went by that had those defects on there or not? And when you divide A into B, those two, you basically get defects per unit, right? After that, for each particular unit, how many opportunities for defects were occurring per unit? So an example here is, if I have an invoice, it could just be good or bad, but you might also have 15 different fields on there that you could possibly have a defect. That is an example of an opportunity for a defect per the unit. So when you multiply that by your total units, you get total opportunities for a defect that can occur on any given invoice. And then you take your total defects and divide it by B times C to get what's called the defects per opportunity. This is a critical measurement for Lean Six Sigma, because when you do that, then you start to understand kind of your percent defective, essentially, right? And then another thing that they do in Lean Six Sigma is they take that DPO, or defects per opportunity, and they multiply it by 1 million. Now, this might seem silly to do this, but the reason they do it is to basically show you and to exacerbate the problem, to say, listen, if you produce 1 million units, maybe it's 1 million loans, maybe it's 1 million batteries or 1 million loaves of bread, for every million, the number that you create here, the DPO times 1 million, you might have 500,000 defects. It just starts to put things into perspective, just how bad your process could be. Okay, and so even in worlds where airline industry and other areas where you have a really robust process, usually not a lot of defects, this, by multiplying by 1 million, it really starts to highlight how many problems you have that you need to fix no matter what. Okay, so hopefully that makes sense around calculating DPO and, of course, DPMO, defects per million opportunity. So now that we calculated the DPMO for a particular process, and again, it's a discrete data process, you can actually get a sigma score. Okay, and so in the Lean Six Sigma world, the sigma score, as you can imagine, is a very important metric to help describe the performance of a process. Okay, and so sigma z is actually a metric. It's a dimensionless metric that allows you to compare one process to another. You might have 50 different processes in your company or manufacturing plants, and you can basically compare them against each other when you get this type of a metric. So, but sigma z is basically the same as saying sigma. And not surprisingly, it's also related to DPMO, which I'll mention in a moment. But sigma z is equal to basically the customer tolerance of variation on a specific characteristic. So let's say it's cup of coffee, right? So what's their specification on that cup of coffee? Okay, so that's kind of part of their tolerance of the variation they expect, or that they're willing to pay for and willing to expect, divided by the actual variability of your process. Okay, that will give you a dimensionless metric that we call sigma z. And so, in essence, the higher the sigma, the better you are. If you have a 6 sigma process, well, that's a pretty good process. If you have a 1 sigma process, that's not a very good process. So sigma is also related to DPMO. So if you go back here, if we were to go and calculate the DPMO for a particular process, and we found that it was a 6 sigma process, meaning it's a really good process, well, the DPMO, or the defects per million opportunity of a 6 sigma process, is 3.4. So that means that for every 1,000,000 cups of coffee that this company or this coffee shop would make, 3.4 out of 1,000,000 would be defective from the eyes of the customer. So that, as you can see, is a very, very good process, right? Or at least I think it is. So Six Sigma is obviously a very, very good process in terms of how it's meeting its customers' needs. And of course, the higher the sigma, the better. The lower the sigma, obviously, the worse it is, and the higher the probability of defects if you get a lower sigma score. Okay, so here's a couple of things to keep in mind. So if you look at a sigma z metric of, say, 1.5, so if you have a process that's 1.5 sigma, that gives you a DPMO, right, defects per million opportunity, of 500,000, which basically means 50% of the time you're making a defect. Okay. That's not a good process at all, right? Really, really poor. Contrast that with a higher sigma score process, like I mentioned before, a 6 sigma process, 3.4 defects, which is now the probability of a defect is basically 0.0003%. Okay, that's a really, really high, highly effective and efficient process. So now that we've gone through calculating the z-score or sigma for a attribute data process or a discrete data process, let's look at a couple of the tools that you can use to help kind of measure your business process with attribute or discrete data. One is called a Pareto chart. And so a Pareto chart is actually based on a Pareto principle that was developed, not surprisingly, by a gentleman named Vilfredo Pareto, Italian economist, many, many, many years ago. And basically that principle states that 80% of the issues in your process are typically derived from 20% of the root causes. So this is a really good thing because all you got to do is identify those 20% and you're going to solve about 80% of your issue. Now, it's not an exact science, so don't quote me on this, but certainly almost everywhere you look, this principle exists, whether it's in economics, whether it's in the defects you find in your manufacturing environment, or whatever. And so most of the time, you'll find that at least 80% of your issues are derived from 20% of the root causes. Okay, and this is all over society. In fact, it's even quite a bit larger in terms of 90-10 rule or 95-5 rule. Okay, and basically what a Pareto chart does, and we'll show you this in a moment, it plots the frequencies or occurrences of specific defects, right? Ideally, defects that are occurring in your process. Okay, and then you sort the Pareto chart. This is key. You sort the Pareto chart based on the greatest number of defects to the fewest number, because that now allows you to really quickly see which are the most important ones to focus on. So here's an example of the paper being used by a specific printer. Okay, so you can see, printer number 6 is using 3,500 pages. And right away, you can kind of see what this is a extract of a Pareto diagram. Okay, it's got the frequencies along the y-axis, right? So number of pages is the frequency, and then you've got the individual printers along the x-axis here. And so the red trend line is basically a cumulative percentage. So you can see that once I have all my data, I've got 100% of the defects I measured. So why that's important is that, remember we said 20%, 80-20 rule? Well, if I were to basically say 80% of my issues is somewhere around here, right? 80% is here, and I draw kind of a straight line down here, and I come down, it's basically saying, the 80-20 rule is saying that, printers 6, 8, 10, 9, and 3 represent 80% of my issues. Now that's not quite 80-20, however, that's how you use this trend line. Okay, quite often you're going to see that 80-20 rule pronounced everywhere, but in this case, if you want to focus on 80% of the problem and fix it and improve your process, I simply kind of draw this imaginary line, come across here, and then bring it down, extrapolate down, and these 5 printers, 6, 8, 10, 9, and 3, are the most important to focus on to fix the problem. Okay, hopefully that makes sense. Next, we want to talk about continuous data. Now, continuous data is going to be a fairly popular type of data you're going to get in your process. It's time, it's money, it's dimensions, scale, height, temperature, those sorts of things, weight. And so this actually is a type of data that gives you much more valuable information around the nature of the problem, the nature of your process. You can calculate all sorts of statistics that help you solve and find root causes much easier than typical discrete data. Okay, and we'll show you a bit about that in a moment. Now, let's talk a little bit about the importance of variation and why we need to focus on it. Six Sigma and Pure Six Sigma was really all about reducing that variability. And why is that so important? Well, because the customer tells us what their specifications are, right? They give us that list or that range to say, I'd like a cup of coffee, I'd like it to be no colder than a certain degrees Celsius and no hotter than a certain amount of degrees Celsius. And that's fine. They state that. And they're giving you that variability. But then when you go and measure your process, you start to see, well, how much am I actually meeting that? And it's the variability that the customer feels. So you can see that, most of the time this customer, their needs are being met, but anything that falls outside of the spec limit on the lower and the upper end, it's not meeting the customer specification, right? And so those are instances where you're not meeting what they want. Okay, and so the key measurement of variation in statistics is called standard deviation. And the larger the standard deviation, the more variability there is in the process. Now, standard deviation, not surprisingly, is depicted by the Greek letter sigma. And that's where Six Sigma got its name from, because that sigma represents variability in your process and how well you meet your customers' specifications. So let's talk a little bit more about standard deviation, because this is such a critical concept. Now, we're not going to get into too much statistics in this course, but this is a critical concept that we need to understand a little bit more. So when we say standard deviation, what is it? So standard deviation is actually a measure of what we call dispersion, right? Which is another way of kind of saying the variation around some metric or something, okay? And so standard deviation is actually the distance between the average. So if you look at this distribution on the left-hand side here, okay, in the middle, this Greek symbol mu is your average, right, your mean. And the standard deviation is the red dot, which is basically the inflection point of your data, and it's the midway kind of inflection point between your data, and the distance between the inflection point and your average is considered your standard deviation. That's 1 sigma. 1 sigma standard deviation of your process. That's the same thing. Okay? And it's measuring the spread of your data. So clearly, if you have a really, really variable process, you would expect this distribution to not look this tight. It would be much wider, okay, much, much wider, and your inflection point would be much, much further out. And so therefore you'd have a really, really bad and variable process. Okay. Now that we've covered a couple of basic, concepts of the measure phase, let's get into kind of giving you some real life tools here that you can use to start measuring your business process. So the first is a typical run chart, right? A run chart is basically something that shows you data and how it's changing over time. And remember, we're dealing with continuous data. So this is data that can be put on a scale, temperature, time, money, length, weight, that sort of thing. When you look at that and you plot it over time, that's called a run chart. Hugely valuable to use a run chart to gather process data around your business process, your problem. Okay, you can use it before and after the improvement. Why? Well, because I'll show you. When you do it before and after, you'll see right away the impact that you've had, or the project and the improvements have had on your process, because you've got your baseline and then your future state, and you can see right away the difference. Now, how do you make the run chart? Quite simply, you can do it in Excel. You decide on the process measure that you want to measure. Maybe it's the time, maybe it's the temperature of your coffee, or the volume of the coffee, whatever it is. You decide on that process measure. Of course, it has to be a continuous metric, right? A continuous type of data point. And then let's gather 20 to 25, maybe 30 data points sequentially. Okay, so sequentially, because this is based on time. And then you plot the data. And once you plot the data, there's a couple of things you got to calculate. One, you want to calculate the average, and eventually you're going to want to calculate the standard deviation, just like we talked about. Excel does that quite easily. So why is this important? Well, because there's a couple of rules that you need to keep in mind for run charts. These rules help you determine something to investigate further. So there's a rule around shifting. So whenever you have 6 to 8 consecutive points on your run chart that are on one side of your average or your center line, that indicates something's caused your process to change. There's been an influence in your process. It's something you should ask, why did that happen? And some of the experts in the room might be able to tell you why that happened, because that is not random. That is something has happened to your process. Okay. Trends. You can notice when you plot a run chart that there might be trends. So 6 to 8 consecutive jumps on the same direction indicate that there is some sort of special cause going on that you need to investigate. Okay, and I'll show you some examples of these in a moment. And sometimes you might get patterns where you get 6 to 8 times in a row, you get the same type of pattern occurring. So let's look at this a little bit. So here in the run chart below, we have a run chart of 50 data points. Okay, the average of the data is 53.2, whatever the metric is. Let's say it's temperature. Okay, and in the run charts below, there are more than 8 consecutive points above the center line. So for example, these are both the identical data sets, but the only difference is on the one on the right, you calculate your average and you draw that horizontal line right through there. That's the average. Now, interesting how when you do that, it kind of shows you something, right? It says, wow, there's something. The data points on the far right of the data are much higher than the ones on the left-hand side. So why is that, right? You need to understand what caused that, but certainly by putting it on a run chart rather than looking at it in a table helps you ask those right questions to get to root cause. Okay, so there's some really important rules that you can find through using run charts and plotting them accordingly. So go out and get some of that data for your process as part of the measure phase. Work with your coach to figure out how much to sample, what type of data are you using, and then go and get some run charts and plot them and see what sort of trending you're noticing. But when you do that, there are some cautions you should keep in mind around the data gathering. So if you have to gather a lot of data and you're not doing it all yourself, it's important to maybe write something out. Maybe you have to write out a basic procedure on how to collect the data. Validate that procedure of how you're collecting the data with the subject matter experts of the process itself, okay? And then you might have to train some people on how to gather the data. If they're measuring, let's say, the weight of something or the length of something, maybe it's not the easiest thing to measure, and you'll have to show them exactly the type of measurement you want to get, because you don't want them to do it incorrectly, because that's going to skew your data and cause all sorts of issues in your process that don't actually exist. It's all part of your measurement system, okay? So here's some examples of what you need to do. If you need to, for discrete data, remember that's either good or bad or yes, no, make sure that everyone knows what is a defect. So if it's a cup of coffee and we're saying, you know what, it's a defect if it's a certain color, or if it's a certain, I don't know, well, taste would be a difficult one, but similar in that way. You have to train the operators and tell them what is good versus bad. Maybe you're measuring, the burnt toast or the color of toast that you're making for your sandwich. Well, there's different grades of color that would be acceptable or not acceptable, and you have to tell your operators which ones are defective. Otherwise, the data they gather is going to have variability in it just in their own measurement errors. Okay. And again, if it's continuous data, see if there's a procedure that you need to do to gather to make sure that people have the right instructions to follow to gather the data. Okay. You might need to go in and observe how the data is being collected so that you have some level of certainty with what you're gathering and if it was done properly. So that brings us to the conclusion of our measure phase part 1. It was a fairly lengthy session. However, I hope you found it useful. Certainly, there are lots of different things that you can measure as part of your project and your problem. We couldn't cover every single aspect in this training course. So if you do have any questions at all, most commonly the questions will be related to what do I need to sample, when do I sample, how much to take, and how do I actually visualize that data. By all means, please reach out to your coach in the portal. They'd be happy to help you understand a little bit more around answering some of those critical questions so that you can gather the data the first time the right way and actually gain lots of value in interpreting that data for your analyze phase.